Hello, this is the Photonic RF distribution team, and here's our presentation for Innovation Day 2022. I'm Connor Hernandez.
I'm Nicolaus Jennings.
And I'm Nicolaus Chen.
Okay, so the purpose of our Photonic RF distribution is to show that an optical distribution network has many benefits over an RF system. These systems are typically used to transmit a message or a reference oscillator over a distance and replicate that signal to many different receivers. This device would typically be used for an antenna array where the antennas all need to be synced on the same reference oscillator. Now, the benefits of an optical network over an RF network are that the losses of the optical network are much less over a distance, and in comparison to RF networks, the size and weight are much less for an optical network. And last but not least, the RF amplifiers typically used for the replication of the signal are much more expensive in comparison to the optical system. Now, previous work done on this project have outlined the use of RF over fiber and future telecommunication satellites from Hernandez. They've essentially developed the optical distribution network that our project is based off of. And then Shin has addressed the phase noise of the optical distribution network and proposed a model that can be used to predict the phase noise. So from that are the specifications of our design, with the output frequency requiring a 1 to 30 gigahertz on the output, which also needs to be tunable. The output power must be between 10 and 13 dBm. The phase noise floor must be less than or equal to negative 165 dBc per hertz at a 10 kilohertz offset. The transmission must be done through 100 feet of single mode fiber. The carrier wavelength must be close to 1550 nanometers. The number of outputs must be scalable to up to 1500 outputs, and the component sourcing must all be done in the United States. Here is our proposed device structure. As you can see on the left is the proposed transmitter, which converts the RF input to an optical signal, which is then amplified and put into the splitter architecture, which is what replicates the signal up to the 1500 times. And then the proposed receiver on the right is what takes that optical signal and converts it back to an electrical signal. Here is our block diagram again, overlaid over our system as we have it at this moment. Here you can see the inputs and the output, just to get an idea of how everything looks.
Before we talk about our transmitter, we need to discuss what dBm is. dBm is just the power level reference to 1 milliwatt. So for example, our laser is an output of 19 dBm, which is around 80 milliwatts, and our EDFA can output up to 1 watt of power, which is 30 dBm. In our transmitter, we have 3 blocks that we're concerned about: the laser, the modulator, and the amplifier. Starting off with the laser, we found that through our testing it was around 1555.9 nanometers, which is okay. We did more testing to confirm any wavelength dependency within our system, as well as we found out that the output power was around 19 dBm, just like specifications stated. Moving on, we have our Mach Center modulator, which allows us to input a light signal and an RF signal and modulate the RF signal, modulate the light signal with our RF. We anticipate an input frequency of around 0.5 to 15 gigahertz. The frequency will be doubled through the modulator, and we expect the automatic bias controller to hopefully maintain system stability by maintaining a bias point. The fiber tap will be used for feedback control on the bias controller. Finally, the amplifier itself will be used to amplify the modulated signal from the MZM, and it will boost the power up to around 27 dBm. This uses erbium doped fiber, which exhibits low losses at this wavelength range.
So yes, coming off the transmitter, we're going to the splitter architecture, which is composed of optical splitters and optical amplifiers. So optical splitters are what you use to replicate the optical signal. That's where we're going to reach our 1500 outputs. But each output from an optical splitter has lower power levels than the input. So that's why the optical amplifiers are required to maintain the power levels. We did do an industry trade study on splitting schemes to determine the most effective combination of splitters and amplifiers. And then after splitters, we get into the receiver. And we're going to be using a photodetector to convert the optical signal into the input signal, into the electrical signal. And our output is supposed to be between 10 to 13 dBm, and we want a phase noise of less than 165 dBc per hertz. And phase noise is just a measure of difference in power at the input frequency and the power at the noise at 10 kHz offset. So we modeled a single receiver output in RSoft, and we got results that showed that our system should work as intended. But in practice, we found that our photodetector doesn't have enough output power. So in this test here, we're comparing our photodetector to the output of a different, well-calibrated photodetector. And yeah, while the waveforms outputs are aligned, showing that the signal actually does go through a photodetector, the power that we got out of it is just far lower than expected. So in conclusion, our system is intended to support distribution of RF signals through fiber in a range of 1 to 30 gigahertz. We examined the functionality of every component in our system, and we only had issues with our photodetector. So going forward, we're trying to find a new photodetector, and we're also considering using RF amplifiers to increase the output power. We're going to want to revisit the simulations with these new components. So yeah, thanks for listening. Is that all we have?